Hello, everyone. In this video, I'm going to be going over my approach to problem 10 in chapter 9 of the Fundamentals of Mass and Heat Transfer textbook. So this problem says that a number of thin plates are to be cooled by vertically suspending them in a water bath at a temperature of 20 degrees C. If the plates are initially at 60 C and are zero point 0.1 meters long, what minimum spacing would prevent interference between their free convection boundary layers? So now, first thing I did, I wrote down the values just to help me remember them. Now, one thing that they mentioned is that they're using their free convection boundary layers. So this is free, open convection that just happens naturally due to buoyant forces. Buoyant forces. Now, uh, the boundary layer distance is calculated is equal to x over Reynolds number to the 1/2. However, because this is free convection, the Reynolds number doesn't really work out super well. However, we can instead use this version of the equation where the boundary layer distance is equal to the of the length of the object over the Nusselt number. Now, in this instance, we can use a Nusselt equivalence using the Rayleigh number. There's a constant 0.59, so the Nusselt number is going to be equal to 0.59 times the Rayleigh number to the 1/4 power. Now, the Rayleigh number is equal to the Grashof number times the Prandtl number. The Prandtl number is a material property, which we can find using table A6 because this is water at a known temperature. The Prandtl number is 6.62. And the Grashof number is equal to G, which is gravity, times beta, which is the thermal boundary coefficient, times delta T times the length of the object cubed over the kinetic viscosity squared. So in this instance, since we're dealing with water, the beta is equal to 1 over the temperature of the water, which is going to be equal to 1 over 20 C or 1 over 293 C. Or uh yeah, 293 Kelvin, which is equal to 0.00366 over Kelvin. Delta T is equal to 40 Kelvin. The kinematic viscosity of water at that temperature is equal to 1 times 10 to the negative 6. Then there's also the conduction coefficient, 0.606 watts per meter Kelvin. Plugging in all the known values, the Grashof number is equal to 1.437 times 10 to the 9. So very large number. Plugging that into the Rayleigh number alongside the Prandtl number gives us 9.5153 times 10 to the 9. However, once we put that into the Nusselt number, since it's to the power of 1/4, it gets dramatically reduced so that we have a Nusselt number of 184.271. It's dimensionless. That's just how the Nusselt number is. Without thinking, I kind of automatically calculated the convection coefficient, which is the Nusselt number times the conduction coefficient over the length of the object, which is why I grabbed the conduction coefficient to give us a convection coefficient of 1116.69 watts per meter squared Kelvin. Completely superfluous. I just did that. So plugging the length and the Nusselt number into the boundary layer distance equation gives us a distance of 0.007367 meters or 7.4 millimeters. Since there are multiple plates, we got to be mindful of the fact that this is the distance from the layer to one of the plates. So in fact, we need a minimum distance of 14.7 millimeters in order to account for the fact that there's a gap between plates. So yeah, this is how I went about this problem. I hope that my approach was useful. I hope that this video was useful. And I hope that any other videos that you find are useful on this channel is useful as well.